So let's go back and talk about the acceleration due to gravity again, our lovely friend that we've had with us since the tail end of kinematics. So we know the acceleration due to gravity on Earth is about 9.81 meters per second squared, and then because we want to put direction, we'll put that down. And we've used this extensively already. But when we've taught you this, we've kind of never put little asterisks next to it. So there's some major caveats with that value. The biggest one is that it's actually only true on the surface of Earth. As you can imagine, g equals 9.81 meters per second squared is not valid everywhere. Different planets have different masses. That will change the value of g. And as I mentioned, it's only true on the surface of the Earth. So if we start to kind of, float up into space, the value of the gravitational field strength is going to change. The other thing, and this is the little bit more obscure point, is that 9.81 meters per second squared is sort of an average. The Earth, we always treat it like a sphere, but it's not. It's not. The distance from the center of the Earth to the surface is not a constant. It always changes. So the Earth, it's actually more of like an egg shape. The technical term is oblate spheroid, but egg shape works fine. Either way, that 9.81 meters per second squared is kind of a total average of all those different local values of the acceleration due to gravity on Earth's surface. At the end of the day, we're still going to treat the Earth like a sphere just because that makes life really easy. So here we have the Earth, and we're going to call Earth the source mass. And we're going to look at the gravitational field of Earth, and then we're using the Moon as a test mass. So the Moon's going to experience a force of gravity because of the Earth. Now, there are two ways to determine the force due to gravity. What we've done so far for anything relating to the force of gravity between an object and Earth, we've used the formula for weight, and we've used that Fg equals mg. So we can write the force of gravity experienced by some test mass. We could say that the force of gravity is equal to the mass, and I'm going to put m for the test mass since it's the actual thing experiencing the force due to gravity, multiplied by our value for g. Now, at the same time, we also talked about Newton's law of universal gravitation. So we can have, if we have two bodies interacting, so we got this big G, the mass of the object experiencing the force, the mass of the object producing the field, divided by r squared. Here's the thing. These two are equivalent to one another. They are both the same thing. This really only works if we know the value of little g where we're trying to study the gravitational field. This is more general, but these two are the same thing. So we can kind of combine them together. So I could say that mg, I could say that that's equal to gmm over r squared. And you'll notice that the test mass becomes irrelevant. The thing that's testing for the field, we don't actually need it to determine the gravitational field strength. That's probably a good thing that it's independent of the object that's testing for it. So with those canceled out, we get something that looks a little bit like this. So we get this magnitude of the gravitational field strength equals this gm over r squared. So this is pretty important. So it's important enough that we are going to put it on the page here. So we have this magnitude of the gravitational field strength. This is going to be equal to the universal gravitational constant times the mass producing the field in question, divided by that distance between the centers of the test and source masses in meters. So again, kind of like the force of gravity in Newton's law of universal gravitation, this only gives us the magnitude of the gravitational field strength. So when we're doing anything where there's more than one gravitational field strength to consider, we have to be really careful with directions. And just to kind of highlight again, the gravitational field strength, it can be in newtons per kilogram, again with the Newton to emphasize that we are dealing with a force, or you can use meters per second squared. Doesn't actually matter. So this equation here, this will allow us to find the gravitational field strength anywhere in the universe. Where we get g equals 9.81 meters per second squared on the surface of the Earth, we're using the mass of the Earth, and we're using the mean distance between the center of the Earth to its surface. That's where 9.81 meters per second squared comes from. Now, the gravitational field strength, as I mentioned, because the Earth's surface is not equidistant from the center, the gravitational field strength is going to change depending where you are on Earth. And what you're going to find is that as you move towards the poles, G is going to increase slightly because the poles are actually closer to the Earth, because the shape of the Earth is it's a little bit more bulging on the sides. So our north and south poles, they're going to be closer to the Earth as opposed to positions on the equator. So if we get closer to the center of Earth, G is going to increase slightly. So at the north and south poles, we're going to have a slightly larger value of G, versus at the equator, it's going to be slightly smaller value of G. But and again, that has to deal with the shape of the Earth. For us, though, we're just going to deal with Earth. On the Earth's surface, G is equal to that 9.81 meters per second squared. And just to kind of finish up on this part, these variations in the gravitational field strength, this can also allow us to look underneath the Earth's surface, like kind of underneath the crust. And this variations in G can also tell us about variations of density. And geophysicists would use this information if they're looking for certain materials, like mining for materials or even looking for oil. So they'll have a special device, I believe it's called a gravimeter, and that will detect local variations in the acceleration due to gravity or the gravitational field strength. And that can give them an indication of what give them an indication of what may be underneath the surface, and if that's what they're looking for, then they can start to excavate in that position.